Hello guys again, this is video 3, starting with question 9. I previously recorded questions 1 through 8. I recorded 1 through 4 on the first video. I recorded 5 through 8 on a different video, but unfortunately my computer didn't pick up any of the audio. So if I have time, I will re-record those with audio. If not, I will at least upload the video without audio, which might be a little confusing. But if anyone has any specific questions, they can ask. It all depends on how much time I have. So, going forward, starting with question 9, we're given a parallel plate capacitor. So let me draw this. Alright, this is our positive Q plate. This is our negative Q plate. V naught. That's a voltage drop of V naught. And this thickness is W. And we want to know the magnitude of the uniform electric field. Well, we know our electric field points this way in the gap. And relating electric field to voltage, we know V, or delta V actually, is negative E dotted with delta R. Of course, there's several different ways you can write this expression. So solving for electric field, and again, we're only considering magnitudes here, so I can drop the negative sign. So solving for electric field equals delta V over delta R, where delta V is just V naught, it's given, and our delta R, we're starting from this positive plate to this negative plate, just W. Simple enough, just looking at a relationship between voltage and electric field, and we can find our electric field pretty easily. Alright, moving on to question 10. And this is with a rod. So let me draw my rod really quickly. And for any of you wondering, yes, I do draw these with an actual computer mouse, so that's why I'm a little slower. It's a lot harder this way. Alright, so drawing the given geometry. This is dy, this is y, this is L. H are our dimensions. We are given that this rod has a whole length L, a charge per length lambda. And we want to know the voltage at point P. Alright. Well, luckily we're not dealing with electric field, so we don't have to worry too much about directions or anything. There's no components with voltage. It's just a scalar, meaning it's just a number, no direction. So, we start with our general form, dV equals K times dQ over R, our differential charge. Alright, let's relate our charge to our known variables. We know that our total charge Q is distributed amongst this length L, and we were given that as lambda, our charge per length. And since it's uniformly distributed, we can say this is equal to a little bit of charge, dq, over a little bit of length, dy. And solving this for dq, you get dq equals lambda dy. And now we're looking at r. R is the last thing we need in this equation. R is just this distance. Using Pythagorean's theorem, you just get the square root of h squared plus y squared. So we get dv equals k times dq, which is lambda dy, over the square root of h squared plus y squared. And if we wanted to find voltage, you would integrate both sides, right? V equaling the integral of k lambda dy over the square root of h squared plus y squared. And remember, we're integrating over a rod, with this being our origin. This is 0. We're going all the way down to L, a distance L from the origin. So our bounds of integration are just 0 to L. And that is the proper expression for our voltage. Alright, moving on to the last multiple choice problem. We have this circuit, this complex circuit actually. This is going to take me a little bit of time to draw. We have 1.5 ohm resistor, 2 amps, and feel free to skip ahead to when I'm done drawing the circuit. This is point A, resistor of 2 ohms. Then here we have 1 amp. We have a 5 ohm resistor. Here we have a 3 ohm. And here is our third battery. And we are given that I3 is going through here. Alright, we want to know the voltage drop across this 3 ohm resistor. Well, this is pretty easy. All we have to do is find current I3. How can we do that? Well, I3 is going around this loop. We know this current going through here. So let's just do Kirchhoff's voltage loop rule. Sum of the voltage drops equals 0. Let's start at this point here. You can start anywhere you want. And we're not given this EMF at all. So that will be a little tricky to work around. At least I don't believe we are given it. No, we are not. So let's start. Let's just call this E. Let's call this E1. Let's call this E2. Because we don't know either. Oh, we know this one is 8 volts. Alright, so we have E1. And then minus, because of passive sign convention, 3 times I3. Going here, we have 1 amp going through this branch. So again, minus 5 times that 1 plus 8. Now going around, and that equals 0. And look, we have 2 unknowns in this equation, so this is already getting kind of annoying. But there's actually a lot easier way to do this. If we're looking right here at this junction, we have I3 coming out of it. Here we have 1 amp going in, and this 2 amps goes all the way down here, and is coming into that junction. So if we're looking at how currents go, we know that currents going into a junction have to be equal to the current going out. So that means 2 plus 1 equals I3. So I3 equals 3 amps. Well, that makes this problem a lot easier. We want to know the voltage drop across this resistor. Now we know the current. So let's just say delta VR is just I times R, with our current being 3 amps and our resistance being 3 ohms. That just gives us 9 volts. Alright. So now we're moving on to the bonus, which I don't know if there will be bonus on Friday. It's asking, what is the sign of the voltage difference VB minus VA? So VB minus VA, we're starting at A, and we're ending at B. And I'm just going to go ahead and calculate this voltage drop, because that combines parts B and C into one problem. So starting at A and going to B, so VB minus VA. Remember, this is a delta V, final minus initial. Starting initial, so I'm traveling all the way here. I can travel as many different ways as I want. I could go around this way. I could go around the whole circuit. I could do whatever I wanted. I'll still get the same number. So starting here, we have this battery. It's negative 10 because of its orientation. We have this resistor. We're traveling the opposite direction of the current. So it's going to be a positive voltage drop of 1.5 is our resistance, times our current is 2. And then we're at B already. And this equals VB minus VA. Negative 10 plus 3, 1.5 times 2 is 3, equals negative 7 volts. So that answers to both our questions. The sign of the voltage difference, VB minus VA, is negative, and the magnitude is 7 volts. So that concludes the multiple choice. I will then be moving on to the longer problems.